Okay, so what made me actually do the talk is that I've read about recursion schemes some time ago, and I asked on Twitter, and everyone said that that's an obvious thing people know and they should know, and that's something that a functional programmer learns when they're born. But then I asked some people, some friends, and they told me that they have never heard about it, and I haven't heard about them, and they're super cool, not that hard, I hope. We'll figure it out. So the usual way to define recursion is like that. So you have a recursive data type. So here is a really very basic AST. You have ints, and you can add them and multiply them, right? So you can do two things to them, that's all. And say you have a tree composed of this recursive data type, and you want to print it, so you want to see what this tree represents. So you define a function that for the const elements converts them to a string, and then for plus it adds them, for multiplication multiplies them. And if you do a print, then give it a tree, it'll print it as a string. Easy, everyone did it. But it is possible, maybe, that we can do better. We can use a magic type like that. So instead of explicitly mentioning the type that we want, we just have a generic type parameter here. And this type parameter will represent recursion. So the A corresponds to the expression, but it allows us to do a generic recursion. So it doesn't have to be the expression here. It can be anything we want. So what could that be? Well, we'll come to that in a second, but first we'll prove that this is a functor. So in order to have a functor, we have to define an f-map, and an f-map that abides by some laws. So first of all, we'll define an f-map. So we have a function that we want to apply to each of the cases. So in case of the constant element, we'll just return the constant element. I'll tell you why in a second. And if we have an addition, we apply the function to each of the branches of the addition, and same for the multiplication. So the structure is the same. The reason why we don't apply the f function in here is that const always has an int, and f is a generic function from a to b, so the type wouldn't match if this was b here, so it would constrain the f needlessly for us. And then we have the monad laws. So first law is that the f-map of an identity is the identity, and then the f-map of a composition of the functions is a composition of f-maps. So to prove one, we just put identity as a function f in here. So an identity of a const is const, and the identity of add is an add of an identity of a, which is a, and a in here, and a in here, so we get the left side. So we have to trivially prove the first law. And then when it comes to the second law, we just write it out. So for the left side, I'm just proving it for add, because for const, we don't actually apply the function, so it doesn't matter. So we have it done for us by definition. And for multiplication, it's the same thing. It's just a different label. So we'll prove it for add and call it a day. So we write out the left side of the f-map in here, and then we see that this actually tells us that we can take out the f to the left side. So we have an f-map of an addition of g of a and b of a, and we take out the g again. So we have an f-map of f, of an f-map of g, of the simple type. So we have just proved that. So we have two f-maps equals the composition of the functions. Okay, so this is a function. Functor. We don't actually have to do it in real life because JHC can derive it for us. But since we're all learning here, it's a nice exercise. So we can come back to our recursive type, which seems a bit useless, right? Because say we define a const of 2, its type is an expression of f of a, and then we define an addition of two consts, it has a completely different type, right? So this is, one is inside the other, and here is just one. So we would need a set of functions, an infinite set of functions that could act on on an arbitrarily deeply nested set of f's. I mean, some could use template Haskell for that, but we're not doing it today. Although we could, that could be interesting. We define a fixed point. So this could be similar to what you've seen on the previous talk with the free monad. This is a kind of a similar thing. So the fixed point of a functor, in general, in mathematics, is for a function, it's the value that is not transformed by this function. So say a fixed point of a function x is 0 because f of x equals x of 0 is still 0. And actually any other number is also a fixed point of that function. So it's a value that stays constant. So how is this a fixed point? Well, so here we have a functor, and we have our constructor that wraps a functor that in turn wraps another constructor of the fixed point. And we can label, so this is the record syntax. The only difference between this and that is that this, we get a function for free that can extract that part. But this is exactly the same thing. So why is this a fixed point? Well, we can extract the inner fix from here. So fix f, by definition, is fix of f of fix of f. So we write those two through. So we get fix of f, and then we extract the inner part. So we get another fix of f of fix of f. And you can do it as long as we want. It's an infinite sequence. So we have a type that's actually infinitely recursive. And it doesn't not care if we wrap it in fix of f once more. So if we just started with this and wrapped it, we could still wrap it up one level, and it would still be just a simple fix of f. So effectively for free, we get infinitely nested data types for arbitrary functions. How is that useful? Well, let's say we want in our basic constructor, so without the whole fix magic, say we have an AST like that. So we add two numbers, so two 2's, and then we multiply it by 2. So let's see what the type of just the most naive thing. So fix accepts some functor. So this is a functor. We proved that on the previous slide. So what would a fix of const2 be? Well, the type of that is fix exp, which looks good. I mean, this seems to suggest that no matter how deeply we wrap, we'll get the same type. So we can proceed with that process. So we can take our fix of const2, so our wrapped const2, and take another one, add that, then wrapped the added value, then multiply that with the wrapped 2, and then wrap it all up because the outermost constructor needs to be the fixed constructor, and check the type. And the type will be the same. So now, no matter how deeply we, oh please no. No matter how deeply we wrap, we get the same type. So we can get a single function that does something to it. So what could that be? We could define an algebra, which is just a function that unwraps a constructor, unwraps a functor. So it's a function from a value wrapped into a functor to a value of the same type. And we have our general recursive type. And say we, again, want to pre-print that. So the only thing we can do with the expression and the string to get an output of a string is to take our functor and apply it to the string. So in case of our integer, we just show the integer. So we get the string on the right side, which is good. In case of the addition, we add the two strings with a plus sign and the brackets. The strange thing here for me at the first sight was that you add two strings. You no longer have the values. You no longer have to recurse deeply into that AST. You just add the strings. And here, same for the multiplication. You add the strings. So how do we actually get there? So we have this function, we have the type, we have the AST, but how do we transform this AST with this function to get some kind of a string representation? Well, we use a catamorphism. So what is a catamorphism? It first applies the out function, then fmaps, then applies the f. So it does the right thing, but let's take a look here and see what it does. It starts on the whole string first. So it unwraps using the out f, it unwraps that fix. So we get the multiplication of whatever. We fmap, so we recurse inside the multiplication and we apply the catamorphism again. So again, we unwrap the other end, we fmap, we unwrap, and then we get the const2. So the const2 fmap of whatever of const2 is const2. So we apply our function of const2 just returns a string. Okay, so we recursed into an AST, and then we arrived at the bottommost leaves, and we transformed them into a string. And then we go up from there. So then the add part, this is a string now, and this is a string. So the add only sees the strings. It no longer sees the original values, it sees the strings. So in a way, we abstract the whole recursion out to this as a fold function, effectively. And we only say what we're doing to the elements, and the elements are of the same types. We can not only use the strings, that would be silly, but we could use the same catamorphism that we've just defined, that unwraps, goes in, and then applies the function with a different function. Say we want the value of 2 plus 2 brackets multiplied by 2. So we say that the value of the constant is just that number, and the addition is the mathematical addition, same for the multiplication. So we have the same fixed expression, the same catamorphism, we just switch the function and we get an 8. So we just taught our interpreter how to multiply, and the function that multiplies knows nothing about the structure of the AST itself. The curious thing is that the type here has nothing to do with the types inside the tree. That's just the type of the output. It's called the carrier type. But it can be any type that we get from that algebra, so that function. So we can fold. How about unfolding? It's way less often used, but we still use it sometimes. So we take a seed value and want to create, in this case, a tree from that seed value. So we switch the arrows the other way and we get a co-algebra. So we get a seed value, and from that seed value we get that type in the functor. So the co-algebra in that case, for some I, if I is smaller than 4, it adds 2 numbers, and otherwise if it's larger than 4 or equal to 4, then it just returns that larger or equal number. And we can, for our catamorphism, to get to the anamorphism, we switched the arrows in the types, so maybe we can just do the naive thing and just switch the functions around the fmap. And it turns out we can. So instead of unwrapping and then going in, we first apply the function, then we fmap over that value, and then we wrap it all in the fixed functor, so we get the fixed functor. And we're lazy, so we don't really want to think about the types that are involved here. So we can ask GHC, and has figured out the types for us. So the anamorphism here, it accepts a co-algebra as we intend, gets a seed value and outputs the fixed point functor. So what would that be? So if we do the unwrap on the value of 1, we get an error that we have no show instance. That's me. Perfect. But we already have the printing catamorphism. So we can get this value, we can print over it, and we get that string. So this is what we got from that seed value. And again, in this case, we can switch the coalgebra in here for another function, and we would get another value with the recursion already defined in here. Well, this is all good and all, but in many cases, who would put speakers in a projector? I mean, like, whatever. In many cases, we want access to the original element of the tree. So say we want to pretty print the tree, but also do some optimization or some cleanup as we go along. In our case, we could maybe add all the numbers as we go along if there's an addition, but if it's a multiplication, we want to keep them the same. The naive solution, and that would basically destroy all the benefits of recursion schemes, would be to parse the output. So we pretty printed it, so on each stage we parse it again and we check if it's the original representation, but it's silly for one thing, and also most of the times it's impossible to do to arrive at the actual original form. So we define a thing called error algebra, which is an easy type again. So it's like the algebra. So algebra was f of a to a, but we also carry around this original thing. So the original fixed functor, and we can act on it. So our function in here that can do what I said. So it can add the additions, but keep the multiplications. If it's a constant, it converts it to a string. If it's an addition, it gets the original value. It uses the catamorphism to sum up the underlying subtrees. On the left side, on the right side, we add the value, we convert it to the string. And then if it's a multiplication, it adds the strings. So we don't care about the original value. So instead of 2 plus 2 in brackets times 2, we got 4 times 2, so it works. And what does it do? Again, it does some of the most obvious things possible. So as with the algebra, we unwrap first, then we fmap with some function, and then we apply our function to the result. So this is the only thing that changed. So how did that change? Well, instead of just fmapping the tree walking function, we do that, but on the right side, which is our algebra part. But on the left side, we just keep the original fixed point at that point in the subtree around, so that the error algebra has access as the first element of the tuple to the original subtree. So those were pre-academical examples. This one is also, but it's more practical. So we have a square that looks like a rectangle, but that's because of the font. We have a square and we want to rotate it 90 degrees clockwise. So the rows become columns. So the first row becomes the first column, then the first row from the bottom. Then the second row becomes the second column, and so on and so forth. So we rotate it 90 degrees. There is a lot of ways to do that, but we can define a recursive data type, define a function that we apply to each of the elements, and suddenly the rotation becomes really easy. So let's define a quad tree. So a quad tree is a tree of 4 elements on the nodes, or some values on the leaves, or just the ends. And again, here that recursion is that general recursion. So we keep that R arbitrary, and we define our helper type quad tree as the quad tree f with the applied fixed functor. So we constrain the recursion inside the fixed point functor. And we have some helper functions that basically construct the nodes for us, and the leaves, the details don't matter. They basically construct those things in an easier way. So we have our original square. So we write it as a quad tree of bools. So the upper left corner will be false, true, false, false. The lower left is false, 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 true. So we go like that. We go from the top left, then top right, then bottom right, and then the bottom left. That's arbitrary, but we chose it so that we can rotate easily. And so on and so forth. So we encode that in that wrapped function. We define a catamorphism. So in order to rotate the quad tree, we rotate it right, and then we wrap around. So this goes here, this goes here, this goes here, and this goes to the beginning. For the leaf, we just take the leaf itself, and we move the empty value inside the empty value just the same way as we did for our cons constructor. And we call rotate on that tree, which is this tree, and it's rotated. So the first row becomes the first column, and the second row becomes the second column, and so on and so forth. So it works. Why does this work? Well, it first takes the whole quad tree, then it recurses in, so it moves the squares of 4 around according to this pattern, and then inside each of the square of 4s, it moves the 4 elements around according to this pattern. So the only thing we actually had to say is that in order to rotate, we permute the elements in that direction. And again, we don't have to define the recursion, so we don't have to, well, there's no possibility for us to make a mistake because the recursion is completely abstracted away. We just say what we did to a single element. So why would you want to use recursion schemes? As I said, there's a less chance of making a bug. In certain problems, not all of them, but some of them, it's easier to reason about the problem if you can describe it with a recursive data types. It is said, but I think it was more true in older GHC versions, or if there's a lot that you do inside that catamorphism or that tree walking function, that it's actually faster to write your data structure using recursion schemes. I've run some benchmarks that this guy wrote, and it's basically the same speed. Maybe it's 20% faster on some very specific benchmarks, but there's basically no difference depending whether you use just manual recursion of various kinds or recursion schemes. So I don't think that the speed argument is a valid one anymore. There's also the side advantage of everyone knowing what the other person is talking about. So assuming people would learn the names of the recursion schemes, we would know how we walk those trees, right? So fold and fold are the basics, but there is probably at least 10 more common recursion schemes. So we have a clear, concise definition of how we walk the trees and what we can see and what not. And a kind of a spoiler, which isn't a spoiler, it's very similar to the free monad. So the only difference, well, the difference between the free monad and our fixed point is that the free monad has this pure part. So our fixed point only terminates when the functor itself terminates. So when the functor has the constructor that is no longer recursive. But the free monad can terminate at any point, even if the original functor never terminates. That's it.
banana?
The quad tree? No, it's from Jared Tobin.
I see. So which one is banana and which one is barbed wire?
Oh, well, so yeah, the other motivation for me was kind of a social one, which is that I read the paper, so you don't have to. I mean, the paper is great and all, but it's very, very dense. It takes ages to get through. So, I mean, you should try it. But I don't know, maybe it's just me, but it's, it was written in 1991. So effectively before we have had Haskell, and also it uses its own syntax for defining everything, or at least that syntax is new to me. So it gets pretty messy. Okay.
Is there a place where those other 10 recursion schemes is nicely explained?
Well, there is Ed Knet's library called Recursion Schemes, and he has a blog post that explains them in a way that he enumerates them with types, and that's basically it. But they are used, a fair bit of Haskell, like the package libraries, uses them. Some of the core ones, I think they're used in text. They're definitely used in pipes. But they're used there because Optimizer was, or still is, I'm not certain, they're better at optimizing non-recursive functions. So, so it can optimize the non-recursive function like this function way better than it can optimize the recursive function. So if this is a complex function, it is possible that the recursion scheme way will be faster than the naive recursion because the recursive part is separate. So it can only optimize this. Well, better. So it is possible that if you do a lot of text manipulation, then you actually get a speed benefit. Because in that morphism, the only thing that was faster with recursion schemes was manipulation of long text and long, very, very long lists.
So you think the hadocs for foldable would have the zoo or a part of it?
Yeah, there is probably around 30 recursion schemes defined there. There is also a zygomorph.
Okay, so on package library.
Well, no, it's called, well, the
traversable, foldable?
Well, there is the data traversable, but the actual package packet is recursion schemes with a dash.
Oh,
yes. And there's even a zygomorphic propomorphism. I mean, they are there. And I think if you're stuck, I was helped a lot by the Haskell IRC channel. So there's a lot of people there too.